Okay, picture this. You're faced with a metal component, I don't know, the size of a small car, maybe even bigger, stretching out longer than a minivan.
Yeah, how do you even begin to think about machining something that massive with any real degree of accuracy?
Exactly. And that's precisely the colossal puzzle we're tackling in this deep dive.
We're putting two heavyweight contenders in the world of machining side by side. You got the Gantry Machining Center, people often call it a GMC, and the Horizontal Machining Center, the HMC.
Right. And we want to get to the heart of which of these, well, these industrial giants truly excels when the projects get really, really big, epic proportions.
We'll be digging into what makes them fundamentally different and, uncovering some surprising strength each brings to very specific kinds of large-scale manufacturing.
So if you've ever looked at a massive piece of machinery, maybe a huge structure, and wondered, how on earth was that made so precisely?
Hmm.
Or maybe you're actually wrestling with machining oversized parts right now, well, then this is definitely for you.
Definitely. And to really understand their capabilities, we've been looking at expert comparisons of GMCs and HMCs.
Okay.
We're focusing on the crucial aspects, the sheer size of what they can handle, their strategies for dealing with, well, just vast amounts of waste material chips.
Yeah, chips are always a big deal.
Oh, yeah. And the practicalities of loading these enormous components, the all-important factor of precision, of course, and where we typically see these machines put to work in different industries.
So what's the mission here?
Our main goal today is really to pinpoint when a GMC isn't just the bigger option, but like the optimal big option for the job.
All right, let's unpack this then. When does a manufacturing challenge really just scream, we need a GMC, rather than, let's bring in an HMC?
Well, the fundamental difference, it often boils down to the sheer scale of the workpiece.
Okay.
While HMCs are incredibly versatile, don't get me wrong, GMCs are generally the better choice for machining exceptionally large components, things that tend to be expansive. We're talking about parts that can sometimes exceed 10 meters in length.
10 meters, that's huge, like machining something the length of a bowling lane.
Exactly. That's a substantial undertaking.
So what gives the GMC that advantage when you're dealing with these truly gargantuan pieces?
It's really a combination of things.
Yeah.
First, the GMC boasts a vast work envelope. It just makes it physically possible to get these enormous parts in there.
Just fitting it is step one.
Right. But beyond just fitting them, there's superior accessibility. You can actually get around these huge components to work on different areas more easily.
Ah, okay.
And critically, the structural rigidity. A GMC can maintain that rigidity across these massive spans, which is a huge advantage.
Why is that so important?
Well, imagine trying to keep something perfectly stable while you're applying powerful cutting forces across, 10 meters.
Yeah, I can see that being a challenge.
That stability in a GMC translates directly into fewer vibrations, better surface finishes on those big flat parts, which is critical for industries like aerospace.
Right, you absolutely need that rock-solid foundation. Okay, so can you give us some concrete examples? Help us really visualize the scale of work here.
Sure. Think about the huge molds used in, say, the automotive or aerospace industries, the ones they use to create large body panels or structural elements.
Okay, like car doors or wing sections.
Exactly. Or consider the wing spars for aircraft that stretch many, many meters. These need incredible precision along their entire length.
Right.
Or picture the massive beds for other giant machine tools themselves. The base of another huge machine.
Machines making machines.
Precisely. These are the types of components that often just physically won't fit within the standardized pallet systems of a typical HMC. It's a literal size constraint, and sometimes weight, too.
So it's not just the overall size, but also whether you can physically load it and clamp it down in an HMC.
Correct.
Now, I'm picturing this GMC.
Mhm.
What does its actual design look like? How does it allow it to handle this immense scale?
Okay, picture a gate, like a big archway. That's kind of the essence of a gantry structure.
Got it.
We have two robust vertical columns, pretty tall, connected by an overhead beam. The machining spindle, the cutting part, then moves along this beam, traversing horizontally across the workpiece.
And the workpiece.
The workpiece is typically secured to a large fixed table underneath that whole structure. So this whole architecture is inherently designed for handling parts of, well, truly monumental proportions.
Okay, that makes sense. So we've got these massive parts being machined, which, inevitably means we're also dealing with a massive amount of chips, all that waste material.
Oh, absolutely. mountains of it sometimes.
How do GMCs and HMCs compare when it comes to efficiently getting rid of all that debris?
That's a really critical point in machining, especially at this scale. Generally speaking, HMCs tend to have a natural advantage in chip evacuation efficiency.
Okay, why is that?
It's primarily due to their horizontal spindle orientation. Gravity basically works in their favor.
Ah,
It just pulls the chips downwards and away from the active cutting zone.
makes total sense. What goes up must come down. And in machining, you definitely want it to go away from the delicate cutting action. Quick and clean.
Exactly.
So what's the challenge then for GMCs? They've got that overhead spindle, right? How does that affect chip management?
Yeah, with the GMC, because the spindle is positioned above the workpiece, the chips naturally fall directly onto the part itself or onto the machine table below.
Okay, so they land right where you're working.
Pretty much. Now, the open design of the GMC does mean that chips are less likely to get trapped against vertical surfaces right near the cut, which can sometimes be an issue in enclosed machines.
So that's a plus.
It is. However, the challenge then becomes managing the sheer volume of chips that have fallen and spread out across this, vast table.
Right, they don't just disappear.
No. Often, these machines are paired with high-volume coolant systems, flooding the area to help flush chips away. And programmers use strategic cutting paths to try and minimize chip accumulation in critical areas.
So it's less about getting jammed up right at the tool and more about the sheer quantity and how far it all spreads.
Exactly. It's a housekeeping challenge on a grand scale.
How do they typically deal with that then across such a large area?
Well, many GMCs are equipped with chip conveyors. They're integrated into the base or maybe around the table to try and mechanically move the chips away.
Okay, trying to automate it.
Right. But honestly, for those really large, relatively flat components, periodic manual cleaning is often just a necessary part of the process, too.
You mean someone literally goes in and sweeps or shovels them out?
You can almost imagine sweeping up piles of metal shavings that could rival, like, small snowdrifts.
Yeah.
It's quite something.
Wow. Okay, so HMCs have gravity as their built-in chip management assistant, basically.
You could say that, yeah.
How does their chip evacuation process typically work then? More detail.
Because of that horizontal spindle, the chips fall directly downwards, usually into an enclosed area below the cutting zone.
Okay.
Contained. Very contained. And that area is usually connected to a highly efficient conveyor system that carries the chips out of the machine.
Much cleaner, sounds like.
It generally leads to significantly less chance of chips being recut, the tool running over chips that are still in the way.
And recutting is bad for the tool and the finish, right?
Absolutely. Less recutting is beneficial for extending the life of the cutting tool and for achieving a better surface finish on the part. It's just a more naturally contained and efficient process within the HMC's work envelope.
Okay. So, while both machines can handle the waste, it sounds like the HMC has a more inherently streamlined and, contained approach to chip removal.
That's a fair assessment.
Now, let's consider the sheer logistics. Getting these enormous workpieces onto the machines in the first place. That sounds like a major undertaking all by itself.
Oh, it really is. You're talking potentially tons of metal.
How do GMCs and HMCs differ when it comes to part loading and setup?
This is actually where the GMC's open architecture truly shines. It is significantly more advantageous for loading and setting up those exceptionally large and, frankly, heavy-duty parts.
More so than an HMC.
Definitely.
Yeah.
Compared to the often more enclosed design of an HMC, especially when you factor in those HMCs with automated pallet changing systems.
Okay, why is that open design such a critical benefit for these massive components?
Well, think about that gantry structure again, those tall columns and the connecting overhead beam. It provides incredibly clear access from above.
Ah, right. Nothing in the way overhead.
Exactly. And often from all sides, too. This makes it much, much easier to use overhead cranes and other heavy lifting equipment.
To just lower it straight down.
Precisely. To precisely lower these massive workpieces directly onto the GMC's large fixed table. It's a much more direct and less obstructed process.
So the machine design anticipates this loading challenge.
Absolutely. Faced with parts that simply wouldn't easily fit into the enclosed space of an HMC or onto its pallet system, engineers developed this fundamentally different, more open approach specifically for that reason.
Okay, I can totally picture the open access being a complete game changer for very large, heavy parts. So what's the limiting factor with HMCs then when it comes to loading these giants?
Look, HMCs are incredibly efficient machines, especially for high-volume production of parts that fit within their pallet system. That's their strength.
Right, the automation aspect.
Exactly. However, when you're dealing with extraordinarily large or maybe awkwardly shaped workpieces that just don't conform to standard pallet sizes, well, the enclosure of the machine itself and the mechanisms of the pallet changer, they can become quite restrictive,
You just can't get the part in easily.
pretty much. Direct access with a crane into the actual machining zone is usually much more limited, if not impossible sometimes.
So it sounds like the GMC's fundamental design is really tailored to overcome the practical, physical challenges of just handling parts that are too big and unwieldy for the more standardized loading systems of an HMC.
That's a very good way to put it.
Okay, let's shift focus slightly. What if the primary goal isn't just fitting the part, but machining these huge components with incredibly high precision, especially if they have large, relatively flat surfaces?
Right.
Which machine is generally the more, let's say, direct and efficient choice then?
Okay, for those expansive, relatively flat components where maintaining high precision across the entire surface is absolutely paramount.
Yeah.
A GMC is often the more direct and efficient choice.
Why specifically for flat and expansive?
It's because its robust gantry structure and that large fixed table provide really consistent rigidity and precision over very long travels. We're talking travels along the X and Y axes, the length and width.
So it stays accurate even when moving way across the part.
Exactly. It's ideally suited for machining those large surfaces without needing complex, multiple setups, which can introduce errors, or needing specialized fixturing that might compromise accuracy.
So it's really about maintaining that unwavering accuracy over those vast distances. How does the GMC actually achieve that level of consistent precision?
Well, think about how it moves. The spindle head, the cutting part, moves along that very rigid overhead beam. It traverses over a stationary workpiece that's securely fixed to the table below.
Ah, the part doesn't move, just the tool.
Right. That design helps maintain accuracy even during very long machining passes. It allows for precise machining of vast, flat, or maybe gently contoured surfaces.
Any other factors for precision on that scale?
Oh yeah. Because of the sheer size of these machines and the workpieces and the long machining times, thermal management is also crucial. Heat expansion can really affect precision.
I bet.
So GMCs often incorporate sophisticated temperature control systems within their structure, like coolant circulating through the machine's frame to help maintain accuracy over those extended machining cycles.
That's pretty clever. Okay, and how does that compare to how an HMC might typically tackle a similar task, say, a large, relatively flat part?
Well, HMCs really truly excel with more compact workpieces that need machining on multiple sides.
It's like a cube shape with features everywhere.
Exactly. Their indexing or rotary tables are absolutely essential for that kind of multi-sided complexity. Think like rotating the part to get to different faces easily.
Right.
So while an HMC can certainly machine flat surfaces, it's not inherently designed for those extreme X and Y axis travels that a GMC handles routinely while maintaining top precision.
They're optimized differently.
Exactly. HMCs are optimized more for precision within a smaller, more contained work envelope, often involving that rotational axis. Parts like engine blocks, gearbox housings, or maybe medical device components with intricate features on multiple faces, that's where HMCs really shine.
Okay, that clarifies things a lot. So it's really about choosing the right tool that's inherently designed for the specific demands of the job. Especially when you get to these massive scales, it's not that one is always better, just better suited.
Precisely. It's about the application.
Now, let's bring this down to, the practical applications. In what specific industries do we typically see GMCs being used as the preferred workhorse for these oversized components?
Oh, you'll find GMCs as the go-to solution in a whole range of industries where dealing with massive parts is just, well, the norm.
Like?
Aerospace is a major one. Think about machining large fuselage sections, those huge wing spars that can be dozens of feet long, or the really robust components of landing gear.
Okay, big airplane parts. Makes sense.
Shipbuilding, too. They rely on them heavily for manufacturing things like large engine blocks for ships and big structural elements for the hull.
Right.
Then you have the whole sector of large mold and die making. This is crucial for producing everything from car body panels to like washing machine tubs, big plastic parts.
Ah, the tools that make other things.
Exactly. And heavy equipment manufacturing, think industries like construction and mining. The machines themselves are enormous, so the parts are too.
Okay, those all make perfect sense given the sheer size of the final products. Are there any other key sectors where GMCs play a vital role?
Absolutely. The energy sector is another significant user. They employ GMCs for manufacturing components for wind turbines, those
Yeah.
giant blades or tower sections,
Yeah, those are huge.
hydroelectric power generation equipment too, and even parts for nuclear reactors.
Hmm.
Very demanding stuff.
Wow.
The automotive industry, beyond just the large molds, also uses them for machining certain expansive engine block designs, especially for large trucks or industrial engines.
Okay.
Even in field you might not expect, like semiconductor manufacturing, you'll find GMCs used to create the large vacuum chambers and other substantial equipment parts required for making chips.
Really? That's surprising.
Yeah, the scale of some of that support equipment is quite large. And finally, the defense industry. They rely on them for machining large military vehicle components like turrets, hulls, as well as sizable parts for weapon systems.
Wow, that's a surprisingly diverse list, but yeah, the consistent factor is definitely the immense scale of the components being produced.
Scale and often the need for precision over that scale.
And just to reiterate then, HMCs are generally more focused on those smaller, more complex, multi-sided parts.
Precisely. HMCs are generally better suited for those smaller, multi-phase complex parts that demand high precision, often in high volumes. Think general precision parts manufacturing, the production of medical devices with intricate geometries, components for electronic products, things like that.
Got it. Different niches driven largely by size and complexity type.
Exactly.
All right, so to kind of wrap up our deep dive today, if you're tackling a machining project and it involves exceptionally large, expansive, and relatively flat workpieces, and these parts require vast travel capabilities, high precision maintained over really long distances, and crucially straightforward loading of truly massive components,
Yeah, that loading part is key.
then the Gantry Machining Center, the GMC, emerges as the clear leader. It's really due to its inherent design. That large work envelope, the ease of access for loading, and the structural stability needed for those extreme scales.
Exactly. It all comes down to selecting the right tool, the one that is fundamentally engineered to meet the specific challenges posed by the size and the geometry of the workpiece you're dealing with.
So when the scale of the project seems almost, beyond comprehension, just remember the gantry. It's a powerful example of engineering innovation, specifically designed to conquer the truly colossal.
It really is impressive technology.
It really makes you think, doesn't it, about what other seemingly impossible manufacturing challenges are being overcome every day with equally ingenious machines out there.
Absolutely. There's always innovation happening.
Well, this deep dive, hopefully, has given you, our listeners, a new perspective, a new lens, maybe, through which to view the sheer size and complexity of the manufactured world around you and the remarkable machines that make it all possible.